This video is brought to you by mywayteaching.com.
In this part, let us study dipole in a uniform external field. In order to understand this concept, you just consider a permanent dipole of dipole moment P in a uniform external field E. Okay. As you can see here, this is a dipole plus Q minus Q, and we are assuming this in a uniform electric field E. Okay. And there is a force QE on Q, and there is a force minus QE on minus QU. So the net force on the dipole is 0. However, the charges are separated, so the forces act at different points, resulting in a torque on the dipole. Okay, these forces or the charges, they act at different points. So it results in a torque, as you can see here. When the net force is 0, the torque is independent of the origin. And the magnitude of the torque, it is equal to the magnitude of each force multiplied by the arm of the couple. So we can say the magnitude of torque is equal to QE into the arm of the couple 2A sine theta. Okay. In general, we can write it as 2QA E sine theta. So its direction is normal to the plane of paper coming out of it. The magnitude of P cross E is also PE sine theta, and its direction is normal to the paper coming out of it. So we can write torque is equal to dipole moment multiplied with electric field, and this torque will tend to align the dipole with the field. So when P is aligned in the direction of E, the torque will be 0. Okay. So this is the case of uniform electric field. If the field is uniform, then the net force will evidently, it will be not 0, right? If the field is not uniform. Again, in addition to that, the torque on the system, there will be torque on the system as on before, and the general case is involved. So let us consider simple situations where P is parallel to E or anti-parallel to E. See, in the first case, this P is parallel to E. Dipole moment and electric field are parallel to E. And in the second case, they are anti-parallel. E and P are anti-parallel. So in either case, the net torque is 0. But the net force on the dipole, if E is not uniform, the net force will exist because the field is not uniform here. If the field is uniform, then only the net force will be 0. And it is easily seen that when P is parallel to E, the dipole has a net force in the direction of increasing field. See, direction of net force and the direction of increasing field. When P is anti-parallel to E, then the net force on the dipole is in the direction of decreasing field. See, the net force is opposite to the direction of increasing field, which means it is in the direction of decreasing field. So the force depends on the orientation of P with respect to E. See, this is a common observation in frictional electricity also. A comb run through a dry air, it attracts pieces of paper, isn't it? And that comb, as we know, it acquires charge through friction. But the paper is not charged, only that comb is charged. That charged comb, it polarizes the piece of paper and it induces a net dipole moment in the direction of field. and that electric field due to that comb is not uniform. Okay. Now let us study about continuous charge distribution. See, we have dealt with charge configurations involving discrete charges, that is from Q1 to Qn, isn't it? Discrete charges. One reason why we restrict it to discrete charges is that the mathematical treatment is simpler and it does not involve calculus. But for many other experiments, these discrete charges are not practical. So we need to work with continuous charge. For example, on the surface of a charged conductor, it is impractical to specify the charge distribution in terms of locations of microscopic charged constituents, which means dividing the space into smaller elements and then taking the discrete charges. It's not practical. So in that case, we take an area element delta S on the surface of the conductor and specify the charge delta Q, isn't it? And then we define the surface charge density sigma at the area element. Okay. This sigma is surface charge density. So we can define the surface charge density sigma as delta Q by delta S. And the surface charge density sigma, it ignores the quantization of charge and the discontinuity in charge distribution at the microscopic level. Okay. And this sigma represents the microscopic surface charge density, which is smoothed out average of the microscopic charge density over an area element delta S. And the unit of sigma is Coulomb per meter square. And similar consideration apply for a line charge distribution and a volume charge distribution. In a line charge distribution, we consider lambda, that is called as linear charge density, which is given by delta Q by delta L, where delta L is a small line element of wire on a macroscopic scale that includes a large number of microscopic charged constituents. And delta Q is the charge contained in the line element. And the units of lambda is given by Coulomb per meter. And in case of volume, we'll represent it by a volume charge density rho, which is given by delta Q by delta V. Okay, where delta Q is the charge included in the macroscopically small element delta V, and it includes the large number of microscopic charged constituents, and the units are given by Coulomb per meter cube. And the notion of continuous charge distribution is similar to that we adopt for continuous mass distribution in mechanics. So when we refer to density of liquid, we are referring to its macroscopic density, isn't it? And we regard it as a continuous fluid. We will not take it in discrete molecular constitution. And we feel due to this continuous charge distribution, even it can be obtained in a similar way as we got it for system of discrete charges. Suppose a continuous charge distribution in space has a charge density rho. You just assume. Okay, it has a charge density, that is rho, and choose any convenient origin O, and let the position vector of any point in the charge distribution be R. The charge density rho may vary from point to point and it is the function of r. Then divide the charge distribution into smaller elements of size delta V. Then the charge in the volume delta V is given by rho into delta V. Okay. You can see line charge, surface charge and volume charge definitions just now what we studied. Now you just consider any general point P with position vector R as you can see in the figure. Okay, then electric field due to the charge rho delta V is given by Coulomb's law, that is equal to 1 by 4 pi epsilon naught Q delta V R dash square R cap. Okay, this is the electric field where R dash is the distance between the charge element and P. Okay, and R dash cap, this is R dash cap is a unit vector in the direction from the charge element to P. By the principle of superposition, the total electric field due to the charge distribution is obtained by summing up of all those things, isn't it? So E is equal to 1 by 4 pi epsilon naught sigma Q delta V R dash Q, just summation. So here P, R dash, R all can vary from one point to another point. So when we delta V tends to 0, as delta V tends to 0, the sum then becomes integral. Okay. Now let us study about Gauss' law, another important law. Let us consider the total flux through a sphere of radius r which encloses a point charge q at its center. Okay, if this is a sphere of radius, we'll consider sphere of radius r and there will be a point charge q inside it at its center. And now you divide the sphere into small area elements as you can see in this figure. Okay. The flux through an area element delta S, electric flux through the area element delta S is given by, so the flux through area element delta pi, as you can see, the flux through this area element is given by delta pi is equal to E dot delta S, which is equal to 1 by 4 pi epsilon naught R square R cap into delta S, where we have used Coulomb's law for the electric field due to single charge Q, isn't it? The unit vector R cap is along the radius vector from center to element. Now since the normal to a sphere at every point is along the radius vector, at that point the area element delta S and R cap have the same direction. Both are having the same direction. So we can write delta pi is equal to Q by 4 pi epsilon naught R square into delta S. Since the magnitude of unit vector is 1 and the total flux through the sphere is obtained by adding flux through all different area elements. Here this one is a very small, only of area element delta S, and this sphere consists of delta S, many delta S. We have to add the flux through each of these area elements, then only we'll get the total electric flux, isn't it? Yes. So now the total electric flux is given by sigma adding all the electric flux of delta S, Q by 4 pi epsilon naught R square delta S. Since each area element of the sphere is at the same distance R from the charge. Okay. This will be equal to Q by 4 pi epsilon naught R square into S. Now S, the total area of the sphere, equals 4 pi R square. We know that, isn't it? So substituting that value, will give Q by epsilon naught. So it is a simple illustration of general result of electrostatics, that is called as Gauss law. So we state Gauss law without proof. Electric flux through a closed surface area S is given by Q by epsilon naught, where Q is the total charge enclosed by S. Okay. So this is what the Gauss law states, that is electric field in a closed sphere S. And the law implies that the total electric flux through a closed surface is 0 if no charge is enclosed by the surface. Okay, in this figure, the electric field is uniform and we are considering a closed cylindrical surface with its axis parallel to the uniform electric field, isn't it? And the total flux pi through the surface is given by pi 1 plus pi 2 plus pi 3, where pi 1 and pi 2 represents flux through surfaces 1 and 2 of the cylinder, and pi 3 is the flux through the curved cylindrical part of the closed surface. Now the normal to the surface 3 at every point is perpendicular to E, isn't it? If you consider normal points to the surface 3, they are perpendicular to E. So by definition of flux, pi 3 will be equal to 0. Okay. So pi 1 is equal to minus E into S1 and pi 2 is equal to E into S1, and S1 is equal to S2 is equal to S. So S is the area of circular cross section. So the total flux is 0. When you find that the net electric flux through a closed surface is 0, we conclude that the total charge contained in that closed surface is also 0. So the great significance of this Gauss law is that it is true in general and not only for simple cases but even for some other complicated cases. So let us understand some of the important points of this Gauss law. The first one is Gauss law is true for any closed surface no matter what is the shape or size. Irrespective of shape and size, this Gauss law holds good. And the term Q on the right side of Gauss law includes sum of all charges enclosed by the surface. The charges may be located anywhere inside the surface. So the total charge is represented by the term Q. In the situation when the surface is so chosen that there are some charges inside and some outside, then the electric field is due to all charges both inside and outside of that sphere S. And the term Q on the right side of Gauss law, it represents only charge inside. It does not represent charge which is residing outside that sphere. Okay. The surface that we choose for the application of Gauss law is called as Gaussian surface. Gauss law is often useful towards a much easier calculation of electrostatic field when the system has some symmetry. In order to calculate the electrostatic field, we apply this Gauss law. It's very simple to use in that particular case.